So now I am going to turn things over to Nashir Contractor. He is the Jane S. and William J. White Professor of Behavioral Sciences in McCormick. And he's also professor at the School of Communication in Kellogg. And he is the director of the Science of Networks and Communities, or SONIC research group here at Northwestern. And if you're a member of NICO, Nashir is a very familiar face, a very prominent figure in the community. So Nashir, thank you so much for being here today. And I am going to turn things over to you.
Thank you, Megan, and welcome to all of you. It's good to see a large turnout, even if it's a virtual NICO at Wednesday without the, so nostalgic waiting in line to get food before we went into the physical facility that we would do there. And I think it's a testament that that says the hypothesis that people came to NICO at Wednesday for the food is not borne out when you have 40 participants here who are feeding themselves. With that said, I'm delighted to welcome my good friend, Tina Eliassi-Rad, to come back to Northwestern. Tina has already presented previously at Northwestern, and we are delighted to welcome her back virtually this time. Tina is a professor of computer science at Northeastern University and also a core faculty member of Northeastern's Network Science Institute, which is very well known and very prominent in the area of network science. Before being at Northwestern, she was on the faculty at Rutgers, and before that, technical member of the technical staff and a PI at the Lawrence Livermore National Laboratory. Tina's PhD is from Wisconsin. In fact, so is her undergraduate, with a brief interlude getting her master's at the University of Illinois, Urbana-Champaign. So Tina has spent a lot of time in the Midwest and has been particularly influential in the work that she's done at the intersection of data mining, machine learning, network science. Her work has been applied to personalized search on the World Wide Web, statistical indices of large-scale scientific simulation data, fraud detection, mobile ad targeting, cyber situational awareness, and ethics in machine learning. In fact, on that last issue, she was just named recently as one of the 100 brilliant women in AI ethics just earlier this year. That was something that is a well-deserved honor. She's also, in addition to her own research, been very involved in terms of professional development issues. She has been a key member of the ACM special interest group focusing on knowledge discovery and data mining, SIG-KDD, to those who are in the know. She's been also a co-chair of the Network Science Conference called NetSci and of the International Conference for Computational Social Science, IC2S2, both of which NICO and some of us have been very involved in helping also move that group. And so we're all very grateful to Tina for her services in those areas. In addition to that, she also won an Outstanding Mentor Award from the Office of Science of the US Department of Energy and became a fellow of the ISI Foundation in Turin, Italy, which for those who may not be familiar, is a very powerful think tank in the area of looking at complex systems and is a very influential entity in that space. So with that very long and perhaps boring introduction, I want to now turn things over to Tina, who's going to tell us something about geometric and topological graph analysis for machine learning. Thanks again, Tina, for joining us today.
Thank you so much, Nash, and thank you so much for that very kind introduction. And thank you to Megan and Andy for arranging this as well. It's a pleasure to be back at NICO. I am going to start sharing my slides, so this beautiful image that I'm looking at is going to go away here. Here we go. And I promise that the talk is not going to be as boring as the title. I know Nash not only gives amazing talks, but also have really amazing titles. I still remember a talk that Nash gave a while back. This definitely was last decade, on some assembly required. So, the titles are really nice. So mine is kind of boring. I apologize for that, but it's going to be a fun talk. So let's get going. So this is work by predominantly my graduate student, Leo Torres, who was going to be here, but his wife is having a baby. So he can't be here right now. Leo is going to finish this year and has already accepted a postdoctoral position at Max Planck Institute for Mathematics and the Sciences. So watch out for Leo. He's amazing. He's a star. And also with two other collaborators, so Pablo Suarez Serrato on the first paper about graph distances, and Kevin Chan from the Army Research Lab on the second paper about graph embeddings. So when Leo joined the Network Science Institute, he came to my office and he was like, well, can we take concepts and advances from geometry and topology and apply them to mining and learning from complex networks? Leo has a background in applied mathematics. And I'm like, this sounds like a good question. Let's see if we can borrow some math and do some graph mining, basically. So what we started to look at, the first thing was graph distances. So I've always been interested in similarity, or distance, if you want, the flip side of similarity, partially because it's an undefined, it's not a very well-defined problem. Also, it has lots of applications. So in terms of anomaly detection, which is the bread and butter of data mining, right? So if I have a series of graphs and I want to see if there is an anomalous graph, like if I have a series of communication networks and I want to see if there is a communication network that is not like any other. The other use of graph distances is, for example, if you have a bunch of graphs or networks, and my apologies, I will use these terms interchangeably. I understand that graphs are mathematical structure and networks are instances that we see around. But you can have a bunch of graphs that you want to classify, right? In particular, this is where if you have a bunch of molecule graphs, like chemical molecule graphs, and you want to be able to classify them or cluster them, you can also use graph distances. So this notion of distance is very prominent in machine learning and data mining, and we love graphs and networks. So what would be a good graph distance? And in particular, because the problem is not well defined, there's lots of them out there. So we wanted to see if there's any advances in particular topology that we could use to say, oh, I'm standing on the shoulder of these topologists in terms of this graph distance. And then if I have time, I'll describe a little bit about the embeddings. So the portion on graph distance starts with this concept called the length spectrum. And then I'll have a slight detour in the non-backtracking matrix. For those of you who dream, sleep, eat, drink networks, usually you think about adjacency matrix or the Laplacian matrix, but not the non-backtracking matrix. So I'll talk a little bit about that. Then I will introduce our distance function called the non-backtracking distance and some properties and examples of it. Since I know it's easy to zoom out of Zoom, I'll give you the spoilers up front. And then if you want to take a nap, you could take a nap until the next set of spoilers. So first, from mathematics, we borrow this term length spectrum. And what we saw was that the length spectrum of an unweighted graph will characterize its two-core uniquely up to isomorphism. So at this point, you might think, oh my gosh, this length spectrum must be an infinite mathematical construct, right? Because if I take a graph and I shave out its tree-like parts, and the reason we have to shave out its tree-like parts is because we're dealing with topology, and in topology, they're interested in cycles. And so a tree is not a cycle, doesn't provide a cycle. So I'm going to tell you about this length spectrum where, given an unweighted graph, we're going to shave it down to its two-core. And then the length spectrum of that two-core uniquely identifies this unweighted graph up to isomorphism. So it's a very powerful mathematical construct. Then in terms of networks, I'm going to show you how the eigenvalues of the non-backtracking matrix track important descriptors like degree distribution and triangles. As we all know, in social networks in particular, the two dominant processes are preferential attachment, which leads to heterogeneous degree distribution and forming of triangles. And then finally, in terms of machine learning, I'm going to show you how the eigenvalues of this non-backtracking matrix give us a great way of measuring distances. So these are the spoilers for the graph distances, length spectrum, non-backtracking matrix, and the eigenvalues of the non-backtracking matrix. So as I already mentioned, the length spectrum of a graph takes a graph, it shaves its tree-like parts, so it's dangling edges. You get the two core of the graph, and the length spectrum of that two core identifies it up to isomorphism. We were able to derive this result by a paper that was published in 2018 by Constantine and Lafont, where they showed sufficient conditions for the isometry of two one-dimensional metric spaces, and that isometry would induce an isomorphism. I won't go through the boring math of how we went from the Constantine Lafont paper to actually showing that the two core of a unweighted graph, the length spectrum of that is uniquely identifies it up to isomorphism. Suffice it to say, we spent a good 6 months to a year just looking at that paper and going over it. But what I'm going to do is I'm going to tell you what this length spectrum is and how you construct it, and that will give you an insight into what I'm talking about. So I have this graph. It has a bunch of nodes and edges, and I'm going to pick a node V. I can pick any node V. In fact, to do the length spectrum properly, you have to look at every node. So we're going to start with a node V, and what we're going to do is we're going to consider the set of all closed walks that start and end with that node. And in particular, right, they're closed walks, which means that I have to get back to V, right? So I'm going to consider the set of all closed walks that start and end with V. Then what I'm going to do is I'm going to create these things called equivalent classes, which is of all the closed walks that start and end in V, I'm going to group them into these classes, which I'm going to call equivalent classes, if they differ only by their tree-like parts, but those tree-like parts don't go through the base point. So I believe you see my cursor here. So these two closed walks that started and ended at V, that is, I started here, I went to this node, followed to this, back here, up and over. These two sets of closed walks are similar, except for this dangling edge that this walk has compared to this other closed walks. So by doing this, I first pick the V. I find the set of all closed walks that start and end with V. Then I group them into these classes based on the fact that they only differ by their tree-like parts that don't go through the base point. So now I have my equivalence classes. Then what I do is from each equivalent class, I pick the shortest closed walk in that class. So if I look back here, I see that in this equivalent class, the one on the top has a shorter walk than the one in the bottom. Or in this one, I see that the top one, again, is a shorter walk than this one. That is, it took less hops. So I find all my closed walks that start and end with V. I group them into these equivalence classes where they only differ by the tree-like parts that don't go through the base point. Then I pick a representative from each of them. Think about your representative in Congress. I pick a representative. That representative is the shortest closed walk in each of these subsets. Then I'm going to put these shortest closed walks all together, and that set of representatives is going to be my fundamental group. The term fundamental group is actually from homotopy. And so then this would be the fundamental group of this graph G that you gave me and the base point V that I picked. And it is referred to with pi of 1. It's in terms of its notation if you look at the homotopy literature. So the fundamental group requires a graph and this node V. Now, as a computer scientist, I don't want to have to go through all the nodes. That's just too much. In particular, I like to work with bigger graphs, and I don't want to go through all the nodes and find their fundamental group. So I will do what computer scientists are really good at, which is bastardizing concepts. So what I will say is that, I'm going to find the closed walks, and I'm going to put them into these equivalence classes, but I'm going to butcher what equivalence means. Equivalence here means that they only differ by their tree-like parts. I'm going to get rid of the notion of this base point. And by getting rid of this notion of the base point, what then I'm looking for is just all the non-backtracking cycles in this graph G. Remember, I was doing this closed walk, and this walk could not backtrack. So there was a key thing about not being able to backtrack. So I can't go from node I to J and immediately back to I. I can go from I to J to K if K is not the same as I. So now my problem in terms of this length spectrum is to find all the non-backtracking cycles in a graph. And then the length spectrum is actually defined on each of these closed walks, and it just measures the length of the shaved version of that closed walk. So here, for example, and it's oftentimes noted as L. So I give a closed walk to this length spectrum, and it says, oh, if I shave this closed walk down, that is, get rid of its tree-like parts. Again, we're getting rid of the tree-like parts because we're looking at topology. Topology cannot deal with these tree-like parts. So the length of this is 3. The length spectrum for this one, oh, I'm sorry about this, we'll say 3 again. And then for this one is also 3, because when I shave it's 3 it's tree-like parts. Again, it's 3. So now I told you how I find the length spectrum. It's a modified version of the length spectrum, right? I take a graph, I find all of its non-backtracking cycles, and then I count them, right? I count how many of the non-backtracking cycles I have of certain lengths, basically. So now the problem is, how can we measure distance between two graphs with their length spectrum? And so what we're going to do is we're going to make 2 assumptions. One is that this length spectrum is a good representation of the graph that I'm going to take. And so then the problem becomes, how am I going to compute this length spectrum, and how am I going to compare the 2 length spectrums? So what we're going to do is, if you think about the length spectrum function again, what it does is it just measures counts, right? So I don't really need to compute all the non-backtracking cycles and put them in a database and then go through them. All I need is their counts, not the actual subgraphs. So that's what we're going to do. What we're going to do is, instead of, even though here it says inputs, we're going to take a graph, and all we're going to do is we're going to find how many cycles of length 3 it has, how many cycles of length 4 it has, how many cycles of length 5 it has, so on and so forth. So in this case, the length spectrum of this graph just becomes a histogram of the cycles, the non-backtracking cycles that this graph has. And so then the question becomes, how do I compute this histogram, right? So, because if I can compute the histogram, then I can compare the histograms, right? So what I'm going to do is I'm going to take a detour through the non-backtracking matrix because the non-backtracking matrix can easily give me this histogram that I'm looking for. So for those of you who don't know what the non-backtracking matrix is, it's a 2m by 2m matrix where m is the number of edges that you have in your graph. So for every direction of an edge, you are going to have a row, and for every direction of an edge, you're going to have a column. And the non-backtracking matrix is a binary matrix where you're going to have a 1 only if you can go from a node I to a node J to the node K and I are not the same. So in this example, I can go from red to blue, and remember the indices here are edges. So I go from red to blue and then blue to yellow. This is a non-backtracking walk, and so I will have a 1 corresponding to that structure in this binary matrix. Now, if I go from red to blue and then blue back to red, that would be that is not a non-backtracking walk, so I will have a 0 there. Now, if you look at this, this is the unnormalized transition matrix of a random walker that can't go back. So it's walking along, and when it traverses an edge, it can't immediately go back. So I have this matrix, and one of the things which I can do is if I take this matrix and I take powers of it, I can find the number of non-backtracking walks of a particular length that start at one edge and end at the other edge. So if I take this non-backtracking matrix and let's say I take it to the power of k, and I look at the entry there after I do my computation at the E1, E2, edge 1, edge 2 entry, that gives me the number of non-backtracking walks of length k because I took the b to the power of k. So this makes me think that, oh, if I were to just look at the diagonal entries where I'm looking at my source being edge E1 and my target being edge E1, then what that gives me is a number of non-backtracking cycles. And again, remember, we're looking at topology, so we're interested in cycles and holes. So what I can do is take b to the power of k and then look at all of its diagonal entries, take the sum of that, and that gives me the number of non-backtracking cycles of length k that is in this graph. Seems nice. Now, because I'm looking at the diagonal and I'm taking the sum of the diagonal entries, that's just a trace of the matrix B to the power of k. So if I take my non-backtracking matrix, I take it to the power of k, and I take its trace, that gives me the number of non-backtracking cycles of length k. So if I were to take the cube of B, and take the trace of it, that gives me the number of non-backtracking triangles because a triangle has length k, which is 3. Now, knowing our nice linear algebra, right, we know that I can compute the trace of a matrix by looking at its eigenvalues. So all I need to do now is just take B, find its eigenvalues, and if I'm interested in the number of non-backtracking cycles of length k, just do a sum over the eigenvalues of B to the power of k. And if I do this, I can easily find the number of non-backtracking cycles of various lengths, of length 3, triangles of length 4, rectangles, length 5, so on and so forth. So then I can do this for both G and H. So now that I have these histograms, how would I compare them? Well, I have these two graphs. What I can do is I can find the cumulative density function, the CDFs, of their respective spectral densities, right? Now, one of the things is that I don't want to find all of the eigenvalues because of the computational cost of it, the runtime of it. So what I'm going to do is I'm just going to find the largest R eigenvalue. Now, this R I can either set, and we have lots of experiments in the paper that talk about this hyperparameter R and how you would set it, so on and so forth. Alternatively, what you can do is set R to be the number of eigenvalues whose magnitude is larger than the square root of the lambda 1. The lambda 1 here is the largest eigenvalue of the non-backtracking matrix. And there is some nice result in terms of why this R is interesting. In terms of basically, if you just look at the top R eigenvalues whose magnitude is larger than the square root of lambda 1, you have captured a lot of the variance in the graph that you're looking at. Now, the one thing is the non-backtracking matrix is not symmetric. And so when you take the eigenvalues, you can have complex numbers. And so there's some details about how do you deal with the complex numbers. So, but given that I have these CDFs, these cumulative density functions, then what I can do is I can just use the earth mover distance or the Wasserstein distance, and that's what I'm going to call the non-backtracking distance. So in particular, to compute the non-backtracking distance, all we do is you give me two graphs, you give me this integer r in terms of how many eigenvalues should I look at, or I can pick the r, which is the number of eigenvalues whose magnitude is greater than the square root of lambda 1. Then what I do is I shave the two graphs you gave me so that they have no dangling tree-like parts. I compute this non-backtracking matrix for both of them. I find the eigenvalues up to r, and then I do the earth mover distance. So very easy. The runtime complexity of computing B, that's one of the issues here. It's m, which is the number of edges, plus n, which is the number of nodes, times k squared, which is the second moment of the degree distribution. Now, depending on how you give me your graphs, I can also make the runtime of computing be less. But this is the general big O for what this graph is going to look like. Now, m in real world networks is usually n log n. So every node on average has degree log n. So every node on average has log n friends. So now, what are some of the properties of this distance function? In fact, we have funding from National Science Foundation to find distances on graphs that are metrics. Now, our non-backtracking distance is a pseudometric, and it's not because it fails triangle inequality. What it fails is the identity of indiscernibles. That is, I can have two graphs whose length spectra are exactly the same, but the graphs are not the same. And this is where we get into this problem of co-spectrality, which is I can have two graphs that have identical spectra, but they're not the same. And the graphs that you're seeing here are the smallest co-spectral graphs with respect to their non-backtracking matrix. This co-spectrality issue can also hold when you have adjacency matrix, when you're representing your graph as an adjacency matrix, or when you're representing your graph as a Laplacian matrix. So if you are using the spectra of the graph to set it apart from the spectra of another graph, you can have this issue of co-spectrality. Now, there are results in terms of graph theory, which shows that almost all trees are co-spectral. There is an open problem about how many graphs are co-spectral. And then there's a conjecture that as my graphs get bigger and bigger, the chance of running into a pair of graphs who have the same spectra, but that they're different, goes to zero, that there are very few of those graphs where they're large and they have exactly the same spectra, but they're different. So we're not that worried about it. However, we cannot say that our non-backtracking distance is a metric, because it is not. It does not satisfy the identity of indiscernibles because of this co-spectrality. So whenever one introduces a new distance function on graphs, it's interesting to look at some of its properties. So what are some of the properties of the spectrum of B based on hubs, right? We, in network science, we really care about hubs, preferential attachment kind of stuff. So I'm showing you some results based on the configuration model with a power law degree distribution. The graph has 10,000 nodes. The average degree is 10. The exponent of the degree distribution is 2.1. And so what I'm showing you is the real part of the eigenvalue and the imaginary part of the eigenvalue. Again, remember, B is not symmetric, so you're going to have imaginary parts. So one of the things that we wanted to see was that as I get fewer and fewer hubs, right, as I get fewer and fewer Beyoncés in my graph, what would the graph look like? What would the eigenvalues of this B look like? And one of the things which is interesting is that as you get fewer and fewer hubs or stars, if you want to think about it, your imaginary part goes away. So, which is actually kind of cool. So the imaginary part of the non-backtracking matrix's spectrum goes away as you get fewer and fewer of these unicorns like Beyonce's or, these kinds of stars. The other thing is triangles. So, right, we all know and love triangles. Friend of a friend is a friend kind of a thing. So here I'm showing you an Erdős-Rényi graph. Again, it has 10,000 nodes. The average degree is 10. The exponent is 2.1. And so again, real part of the eigenvalue and the imaginary part of the eigenvalue. As I increase the number of triangles, the nice circle that I had around the origin goes away. That this nice pattern that I had about the spectra and where the eigenvalues would fall disappears. And in fact, there are results in terms of looking at the eigenvectors of these eigenvalues. And so the eigenvectors of the non-backtracking matrix, the first one and the second one, tell you about edge centrality and also the modularity of the graph. So in terms of experiments, we looked at lots and lots of different data sets. We looked at a whole bunch of synthetic data sets, Barabashi-Albert, configuration model, ER, Kronecker graph, Wetzel graphs, hyperbolic graphs. Then we also looked at online social media networks like Facebook, e-opinions, Twitter, Wiki. We also looked at co-authorship networks. We separated them out because co-authorship networks, as you know, they're projected bipartite networks. And so they really should be treated differently than naturally occurring social networks that are unipartite. We also looked at peer-to-peer networks and also autonomous systems networks. And so one of the things, just as a sanity check, was that if I were to rewire the edges of a graph, what happens to the distance measure? So what I'm showing you here on the x-axis is a percentage of the edges rewired. On the y-axis, I'm showing you the non-backtracking distance. And as expected, as we rewire the graph more, the distances becomes bigger. And the distance here is comparing the original graph to the rewired graph. So just a sanity check, a kind of a unit test. Then the other thing that we wanted to look at was of all of these synthetic graphs that we have, right? Barabashi-Albert, Kronecker graph, hyperbolic graph, so on and so forth. Where do their eigenvalues fall in this real versus imaginary picture? And so what you're seeing here is one dot is one eigenvalue, and R in terms of the number of eigenvalues is 200. And we looked at 50 graphs per model. That is, we generated 50 graphs, for example, let's say from the ER network, and then we found the top 200 eigenvalues in each one of them, and that's what I'm plotting. And part of why this is interesting is just to see where the eigenvalues of the non-backtracking matrix for these random graph models are. And that, for example, we have nothing in these areas of extreme where the real number is very large and the imaginary is very low, or the real number is very large and the imaginary is also very high. And again, this kind of helps in terms of looking at the hubs and the triangles that I showed before. Now, one of the applications that I was motivating was that perhaps what you can do is you can use this to cluster graphs. So what we did was we took these eigenvalues, we ran them through UMAP. UMAP stands for Uniform Manifold Approximation and Projection. It's one of the more recent dimensionality reduction approaches that people use that both look at local and global aspects of your data. And one of the things that we found is that using the non-backtracking matrix and using its eigenvalues is able to nicely separate the synthetic graphs that we have. So where you get a cluster of the Watts-Sograts graphs, you get a cluster of the hyperbolic graphs. There are some mistakes when it comes to the BA, Kronecker, and the configuration model, but we all know that those are very similar. So the fact that this approach is making some mistakes there, it's fine. The one thing is that what I'm showing here in terms of the clusters, again, we're taking the data from the left side, and what we're doing is we're feeding it to UMAP, and then we're plotting the first component vector versus the second component vector. So every dot here is a graph versus in the left side, every dot was a eigenvalue. Oops. We then looked at some heat maps in terms of just seeing what these distances look like. We're looking at distances, and the dark navy is 0. So you would expect in terms of these kinds of heat map matrices that the diagonal would be dark navy. One of the things that, for example, you see is that the social networks are very similar to each other. Their distances are smaller compared to like the CA, the co-authorship networks. The peer-to-peer networks are very close to each other. The autonomous systems network are not as similar to each other. Just some observations based on some of these experiments that we've ran. Then, of course, you always get this question about, like, well, how does this compare to other distance measures or other distance functions that are out there? So what we did was, as you can imagine, there are tons of distance functions out there for graphs. We looked at those that are in the same category. So what I'm showing here in terms of methods, I'm showing the non-backtracking distance where we pick the number of eigenvalues automatically in terms of the top R eigenvalues where their magnitude is greater than the square root of lambda 1. I'm also showing you the non-backtracking distance where we pick the eigenvalues as top 300. That is, just look at the top 300 eigenvalues and then build the CDF on those. Then we looked at the graphlet correlation distance. This is where you are going to extract these graphlets, subgraphs from the graph, and then measure distances based on how correlated those graphlets are. We also looked at the top 300 eigenvalues of the Laplacian matrix, since we're looking at the top 300 eigenvalues of the non-backtracking matrix. We looked at ESCAPE, which is a paper that was published in the World Wide Web Conference back in 2017, where it does motif counting. It can count up to motifs of length 5. And then we also looked at this S distance measure, which measures distances based on the distribution of the shortest path lengths between each pair of nodes. And so what I'm showing you here is homogeneity versus completeness. Homogeneity is like precision. You can think of it in terms of precision. Completeness, you can think of it in terms of recall. These dashed gray lines that you are seeing is called the V measure. You can think of it as the F1 score. So this dashed V line is the V score of 0.85, this one is 0.75, and this one is 0.65. And so I'm showing you the various methods. This is where basically in a data mining machine learning talk, it's like, look, my method beats other methods. And you don't see ESCAPE here because ESCAPE's precision, recall, or homogeneity and completeness was off this chart. And the results here is based on spectral clustering. So we have the synthetic graphs. We know which process generated them. We represent them. We measure distances based on these different methods. We use that for spectral clustering. And then we see how compact and homogeneous, how complete and homogeneous each cluster is. And so we are doing well there. Just to summarize this one part. So Leo walks into my office and says, let's look at this paper. Look how great this paper is. And I'm like, this has to do with topology. It has nothing to do with graphs. He's like, but we can work on seeing if we can take information from here and apply it to graphs. I'm like, okay, let's look at that. That took us like 6 months. Then it's like, oh, well, how am I going to find all the non-backtracking cycles in a graph, right? And then it was like, well, maybe I don't need to find all of them. All I need is the count. So then we stumbled on the non-backtracking matrix. Then we saw, oh, if I just find the spectra of the non-backtracking matrix, I'll be fine. Now, the co-spectrality issue is because of the way we are counting the number of non-backtracking cycles. If I were to use sampling to do the non-backtracking cycles, then I wouldn't have to worry about the co-spectrality issue. But we're not so worried about the co-spectrality issue, again, because there's a conjecture that as your graphs get bigger and bigger, it's rare that their spectra will be identical and the graphs will be different. And we saw that it does well in certain applications. In the paper, we have lots of other applications like anomaly detection on our favorite Enron database, right? We're all sick of it, but we still use it because it's annotated. And the main idea here was that paper by Constantin Lafont and trying to see how we can compute the length spectrum from a graph. The paper is there. The code is also available. You can download it and play with it. I know I'm running out of time. I'll just briefly talk about the embedding. So the thing with the embedding is, I'm sure you've heard about network embedding or network representation learning or graph embedding. So basically what they do here, and I'm only going to focus on the node embedding. You can do edge embedding. In fact, in the paper I just presented, we talk about edge embedding. But you have this graph, it's in high dimensions. And what you want to do is you want to vectorize the nodes. You want to map the nodes into this lower dimensional space. And what the majority of people do is they're mapping it into the Euclidean space. So there has been work in terms of mapping it into hyperbolic spaces. And the general assumption that they make is that if you're close in the graph space, then you should be close in the embedding space. And if I can do this, then I can do node classification. I can do all these kinds of graph issues that I would like to look at. Now, Leo's idea was that, look, if I'm embedding it into this space, there's geometry there, and I should be able to use that geometry and not just look at the distance minimization. And so that was the work that was published in Journal of Complex Networks. We introduced this new embedding approach called GLE for geometric Laplacian eigenmap embedding. And in terms of the spoilers here, from mathematics, we know that there's a bijection between undirected graphs with n nodes and the n-1 dimensional simplices. What we can do is we can encode the graph structure in geometric terms using the simplex geometry of the Laplacian representation of the graph. And what we saw is that some of the very popular graph embedding methods that are being used only do well when you have lots of triangles. So if you're using node2vec or deep walk or any of the random walk-based methods, and also some of the other methods which they just rely on distance minimization, then they do well if you have a lot of triangles in your network. By do well, I mean do well on like link prediction or node classification, but they don't do well if you have protein-protein interaction network, which doesn't have as many triangles. And so if you do take the geometry into account, then you could do well both on networks that have lots of triangles and networks that don't have as many triangles. So lots of details on the second one. I just give you the spoiler in terms of going and looking at it, in particular because embedding is so popular these days. So I presented some of the work of my brilliant student, Leo Torres, in terms of graph distances and embeddings. And the idea was, let's look more closely in the applied math literature and see if we can use ideas from there and operationalize them for graph mining and machine learning applications. So thank you for your attention. Sorry, I went a little bit over, and I'm happy to answer any questions.
Oh, that was very good. Let's see if we can do some way of doing the applause here. I'm not quite sure how that would work, but I'm certainly going to recognize that I'm sure a lot of people would want to be applauding at this point. So thank you again, Tina. That was very good, and it's quite affirming for you that questions that were posed were then subsequently answered by you in slides, even without you looking at it. So Saurav had a question. I'll just recap it in case you want to add some additional comments to it. But Saurav's question was, computing graph similarity via non-backtracking matrices is obviously interesting. And that did you apply this to classify or cluster graphs? And how well does it capture the similarity with respect to known measures such as kernel-based methods, graphlets, subgraph frequencies? And then I think 5 minutes later, he said, she's already on addressing this question on slide 53. So did you, and I know which slide he's referring to, but is there anything further you would want to add to what he presented on that slide?
Yeah. So thank you for the question. Yeah, that was one of the key things in us publishing the work, right? To compare it with others and see how well it does. And so, which we did, and seems to do well. Again, the one thing is, a lot of our experiments were actually on synthetic networks. We had real world networks, but we also had synthetic networks. And in part was because, especially in machine learning and data mining, people treat data as if it came from gods, and they do not look at, well, which part of the distribution did this data come from, right? And for example, when you talk to awesome scientists like Nash, who care about like how the data was generated or collected, then you're like, okay, well, like I have to think about the hearts and minds of these social people in the social network. Or when you talk to people like Vespagiani or Barabashi, they care about the distribution that the data has come from, right? But then when you talk to a machine learning data mining person, they're like, oh no, I got 10 data and this is what my algorithm does. And so we tried to stay away from that, right? We had the real world networks, but we also had all of these different random graph models. And if I didn't include your favorite random graph model, I apologize. But just to see in terms of, okay, what happens if I have a graph that has a lot of triangles, or it doesn't have a lot of triangles, or the degree distribution is heterogeneous, or if it's homogeneous. So that was what we really focused on. And I hope that if there's any machine learning or data mining person that is listening, that really pay attention to the distribution that your data is coming from, and not just think data is coming from God.
Yeah, that's a good piece of advice that helps one discipline appreciate what are the demands and requirements in adjacent disciplines. Rosemary Braun says, thank you for a superb talk. I'm curious about how this can extend to weighted and or directed graphs. And then I'll also put in a sort of more specific question that she had. In the spectral clustering example, there was a large difference in F1 for NBD with R versus 300. Can you comment on the sensitivity? Would you expect that, for example, the Laplacian would also be that sensitive to the number of eigenvalues considered?
Yeah, so both questions are excellent questions. Let me answer the first one in the Q&A in terms of how many eigenvalues to look at. In the paper, we do a complete sensitivity analysis on this hyperparameter. And you will see that the hyperparameter varies depending on the type of network that you have. And so that was part of why we saw this big difference. In terms of so it is a hyperparameter like any other hyperparameter, where like doing sensitivity analysis is a good way of going. We do have a model selection way, seems to be doing okay. In terms of the Laplacian, we didn't try that. That's a good question. We didn't try to vary the eigenvalues of the Laplacian to see if I had picked like 200 eigenvalues, what would happen. In terms of weighted or directed, we haven't gotten there. Again, it's a really good question. I think it's more applicable to directed. I think applying to directed makes more sense. To the weighted, I do not know at all.
Well, I mean, it is a prototypical challenge in network science. Almost everything gets first developed for an undirected binary graph, and then there are extensions that move us into both valued graphs as well as directed graphs. Thomas Whiteock has a question. To what extent does the existence or lack thereof of an edge in a graph impact the graph spectrum?
Yeah, so this is very interesting. So Leo has a paper that just was accepted to the SIAM Journal of Mathematics of Data, where it looks at a node and the effect that a node has, so deletion of a node has on the non-backtracking matrix, not a particular edge. I'm not sure how much a particular removal of a particular edge will have an impact. But the recent paper in the SIAM Journal of Mathematics of Data goes in depth in terms of what happens when a node is deleted. And part of the motivation for that was in terms of immunization. So I will refer you to that. If you can't find that paper, just shoot me an email, or I can try to find it and link to it now and put it in the chat, or put it as part of a Q&A. So excellent question.
So we have a couple more questions, and others might come in as well. But the next question is from Yanchen Liu. How did you solve the problem of overcounting cycles? For example, 2 connected triangles are counted as a length 6 cycle, or cycling each triangle twice is also counted as a length 6 cycle.
Yeah, very good question. So we looked at simple graphs. So let's see, can I actually, sorry, if I may, I found this. So can I ask a question to put in the...
if you can, would it be like type the answer and put it in
yeah,
as an
if I put it in the chat. Okay, sorry. I think all panels can see the chat. So this is the link to the paper for the previous question that was asked about the effect of a node, of an edge removal. And for the full glory of it, see that paper for the effect of a node removal. And that had applications in terms of the immunization. In terms of the counting of the simple versus complex cycles, right? So let's think about what's happening. So I have this non-backtracking matrix, right? And if I take it to the power of k, then I find all the cycles of length 3. And then if I take it to the power of 6, I find all the cycles of length 6, right? And there's nothing in terms of the length spectrum that says that I should only look at simple cycles, or if I should look at complex cycles, right? It says find all sets of closed walks. And so for us, that was not an issue, because what I'm doing by finding the spectra of B is I'm looking at all the complex cycles that exist. So I hope that answered that question. The last one is, what is awesome reading on graph embedding? There's actually 2 papers that recently came out. One in particular for the social scientists in the audience. One is by Denai Kutra, and let me see if I can find it here. I'll put the chat. Because they looked at the graph embeddings and they were trying to understand it based on equivalences from social sciences. So structural equivalences, automorphic equivalences, and regular equivalences. So that's the link for it. And then the other one is an evolving document by a few folks at Google, where they are looking at they call it, I think it's called Machine Learning in Graphs. And the last author is Kevin Murphy. And they have a really nice taxonomy in terms of the different embedding approaches. So I just put that chat there as well. The thing, so we are actually working on a graph embedding, if I may just, I know we're getting close to the end of the hour, but we are looking at graph embedding based on a bunch of criteria. A lot of them look at what does similarity mean, what is the objective function that they're looking at. So for example, there is a deep learning approach called SDNE for stochastic deep network embedding. And depending on how you set its hyperparameters, the results are identical to basically PCA. So why am I not doing PCA and I'm using their deep approach is not clear. So we are working on just trying to pin these embeddings against each other, and also trying to come up with a guide of like, okay, here's the type of graph I have. This is its degree distribution. This is its triangle distribution. Which embedding should I use? I think that would be very useful, and it's something that my lab is working on. In particular, since we found that depending on how many triangles you have, you should be very careful in terms of what graph embedding approach you use.
That's very good. So thank you again. I'm going to hand things over to Megan, who's come on and is eager to close us out here. So take it away, Megan.
All right. Yeah, it looks like that is it for our questions. But Tina, thank you so much. I know, as Nashir said, you can't see everybody clap, but trust me when I say everybody really enjoyed your presentation. So thank you so much for being a part of our webinar series.
Thank you, Megan, and thank you, Nash. It was good to see you. Take care of yourselves, and I hope that our paths cross in real life soon. So
we'll look forward to that. We'll look forward. And thanks to all the audience again for joining us today. And we'll look for you at the next Wednesday at NICO.
Yeah, we'll see everybody next week. Thank you, and have a great Wednesday. Bye, everyone.
Bye.
Bye, everyone.
Bye.